Hello, Houston. We were in the midst of looking at logical reasoning last time, and I left you with a teaser, which I'm going to pick up with today. We're going to go directly to the screen and show you what we were working on last time, and that is in logical reasoning. I told you that I was going to give you the name of a color and a shape. Well, actually, I have written those down secretly, and I'm going to show you shapes like this. This is what Wason calls the fog problem, and it's typical of the generative problems that we were looking at. Last time we considered, for instance, the issue of progressive numbers, the progressive numbers problem. I told you I had a rule, and most of your guesses were attempts to confirm when I told you what a particular correct answer was, 2, 4, 6 being among them. And many of the other guesses were 1, 3, 5, minus infinity, 0, positive infinity, and so forth. And so what we tend to do is have a bias toward affirming what we know for sure. And when it comes time to try and demonstrate the nature of a rule, we carry that affirmation bias into the way we try to negotiate coming to a correct answer. And the answer in that case was any series that advanced, qualified by the rule that I had created in that situation. Wason had another rather intriguing one. This is a bit of a mind-boggler, but it's another issue where you have to look for exceptions and then try to generate your own particular answer. That is, this is a generative problem. And so basically, I'm giving you, or I'm telling you, that I wrote down a particular name and a particular color. And what I'm telling you is that the problem is, if BD is a fog, what can you say about each of the others? Where the solution is essentially that given the color and the shape that I wrote down, to be a fog, you have to have one but not both of the two things that I listed. That is, you either have to have a shape or a color included in order, in the particular example, the particular figure, in order for it to qualify as another fog. So if the black diamond is an example of a fog, what can you say about each of the others? And that puts us into a rather exhaustive but fairly direct series of tests that we can perform. So for instance, if I've told you that the black diamond is a fog, what do we do about the white diamond? Is the white diamond a fog? And the answer is no. Okay? Let's consider what's written down. All right? One color, one shape. If black and circle are what I've written down, then white circle is a fog. Okay? Black circle is not because it has both black and circle. White diamond is not because it has neither. So if we wrote down black and circle, and we've told you already that black diamond is a fog because it's black, not because it's circular, but because it's black, then we can eliminate white diamond because it has both, it has neither, and the black circle has both of the things that I wrote down. Those can't be fogs. So the only other possibility then, if black diamond is a fog, is that white circle is a fog. On the other hand, if white and diamond are what I wrote down, then white circle still is a fog, because in this case it's white, but it's not diamond-shaped. Black circle is not because it has neither, and white diamond is not because it has both. And so basically, consistent with deductive logic here, a specific, necessary, defensible answer can be derived. That is, when I tell you that I've given you the name of a color and a shape, I have written down one of each. And in order to qualify to be a fog, an element has to have one but not both of the two things that I've written down. We can logically work through to a particular specific and defensible answer in that case when I tell you that black diamond is an example of one. What we need then, the only other possibility, is one that has neither blackness nor diamondness. So the only other possible candidate to be a fog under those particular conditions is the white circle. Because again, I wrote down black and circle, making black diamond, black but not a circle, a fog, and the other one would be white circle because it is circular but not black. And so in that case, the definitive answer there, the derivable, decisive, definitive answer can be derived in each case there. Now there are some other biases that are operating in this kind of a situation. Okay? So the solution involves the various kinds of biases that may influence what we've got. One is intuitive errors. That is, you tend to leap to, well, if black diamond is, then white diamond must be, and so forth, or we can, by the same logic, we can go to black circle. But in fact, in that case, you have to get out of that. If black diamond is a fog, then white diamond or black circle must be fogs? No. In essence, what we've got here is an illustration of what is called exclusive disjunction. That is, to solve this one, you have to use the rule of what is called exclusive disjunction, as I've just indicated. To qualify, an object must have one or the other feature, but not both. Let me show you another example where we end up with a particular kind of interesting bias that creeps in here. This is the same kind of problem done in a slightly different way. Using, again, the rule of exclusive disjuncture, try this one. Another example of a generative problem is what is called the half-sisters problem. I'm going to give you the following. Okay? My mother and father are divorced. Each has remarried, and about that, I will tell you that Steve is not my father, and Beth is not my mother. So in essence, Steve and my father are two different men, and Beth and my mother are two different women. Given those premises, which among the following would be a half-sister of mine? So here's the same conditions that I just spelled out for you. Now let's look at each of the following. The problem is, among the following, who are my half-sisters? Who is, I should say, each individually. Which of the following is a half-sister of mine? And what we'll tell you is each of the following. We've got Trish, whose parents are my father and Beth. Carolyn, whose parents are Steve and Beth. We've got Mary, whose parents are my father and my mother. And Yulisma, whose parents are Steve and my mother. Steve or Beth or my mom and dad have been pretty active, I guess. But the question then is, among those four people on the left, who would qualify as being half-sisters of mine? Any guesses? What does it take to be a half-sister? Yeah, we have to share one parent in common. If it's both parents, what's the product? What would that person be? This is not hard. Don't make this hard. If we share both parents in common, such a girl would be my sister, a full sister. If they have neither parent in common, they're unrelated. They're a zero sister. They're a non-sister. Okay? So in this case, we've got that exclusive disjunction rule again. The parents have to be either my mother or my father for a female to be my sister. And so if you consider that in this situation, who are the two candidates who are, in fact, there are two half-sisters in that list. Who are they? Trish is one.
Trish and Yulisma.
And who's the other one?
Yulisma.
Yulisma. Because in each case, those two share I share with those two people one parent. But with the other two, Steve and Beth are not related to me, and my mother and my father both are related to me, and thus can only produce full brothers, full sisters for me. Now the interesting thing is that is exactly the fog problem specified in a different way. Those two problems that I've given you are identical. The fog problem and the half-sister problem are, again, using the rule of exclusive disjunction. They both use exactly the same thing. Interestingly enough, one group of investigators, Smith and Clark, gave this problem to students, the fog problem, to students, and what they found was they gave the half-sisters problem, and then they gave the fog problem, even priming them without telling them specifically that the two problems were identical. And what they found was rather interesting. When it was expressed in the form of half-sisters, 94% of the people who were given that problem could solve it. That is, after thinking about it a little bit, they could work out the rules that we did in class here. That is, that one of my parents, but not both, would participate in producing half-brothers, half-sisters for me. Interestingly, though, having solved that problem, only 12% of the people were able to solve it when it was done in the form of the fogs that we were talking about a minute ago. Although the exact same rules qualify and apply in both situations there. The point there is that essentially the absence of an applicable model makes any problem much harder to solve. When you're dealing strictly with shapes and colors, it's a lot harder in the abstraction to figure out what the relevant rules are there, and yet when we're dealing with mom and dad and two other people, we can very easily figure out, well, that's a half-sister, that's not a half-sister, that's no sister, and so forth and so on. So that under certain conditions, we're going to come back and look at this a little bit later, but there are certain ways, certain parameters that we can apply to problems that will in some cases make the reasoning that goes into solving them a lot more obvious and a lot easier to achieve, as we'll see here. For right now, let's jump over and look at another process called reasoning and recursion. Recursion is kind of it's essentially a mental sinkhole if you get into it. I'll give you a very specific example of what I mean here. Unlike many of the sources that I've cited in the lectures here, this one I'm going to read the entire article for you. I'm going to take a reference here and I'm going to read the entire thing to you, and it won't violate any copyrights. John Morton, in 1976, published an article in which he wrote, and I quote directly, "Further details of this paper can be found in Morton, 1976." And then he referenced himself, which means then that you go look up Morton, 1976, and what you find is an article, the entirety of which is, further details of this paper can be found in Morton, 1976. And of course the details that he's referencing there are the fact that he's referenced himself, which makes it a kind of an infinite loop. And if you get into that too far, you're going to waste an extraordinary amount of time, because in that case you have to kind of get outside the loop to really begin to understand what's happened. But he has referenced himself, which makes it essentially an infinite loop. There's more details in Morton 76. Well, let's check Morton 76, who suggests Morton said, you never get out of it. Another example of this, which may be a little more familiar to you, is what's called the liar's paradox. And the situation that you face here is the following is the liar's paradox, and this has been with us for a long time. Epimenides, the Cretan, is credited with pronouncing factually whoops, I've skipped out of here. Well, let me just read this one to you. I thought I had some illustrations for it here, but in any case, what he gave was, all Cretans are liars. But Epimenides is himself a Cretan. Thus, when he says all Cretans are liars, is he himself lying or not? So again, you've got a kind of a mental sinkhole. You can get into that a long, long way, and yet, if we can demonstrate that he is not lying, then in fact what we've done is to essentially disprove his initial assertion. So if he speaks the truth, he's lying, but if he's lying, then he speaks the truth. And there's no way to get out of that box. But in essence, what we're dealing with there is that it's necessary that you have to consider it. What you basically have to do, the solution in this particular case, is metacognition. You have to think about thinking, and you have to step outside both of those last two problems actually to solve them. You have to realize the impossibility of responding to the premises that are put in there. And so basically the solution in those two cases is metacognition. You have to think about the nature of the problems that you're talking about in that situation. So just because we're talking about logical reasoning doesn't necessarily mean that logic dictates in all of these situations that we might cite for you here. So I was jumping into another problem here. Let's consider this. The two letters problem, which is another example here of kind of the liar's paradox in a slightly different form. I'm going to give you here two letters, A and B. And the rules that are going to operate here are the following. B can be replaced by BC. So we can immediately get to ABC if we want to. A second rule is any letters to the right of A may be doubled. So we could immediately go to ABB if we wish to do that. BBB can be replaced by C. So if we find a situation where we get BBB, we could then make a C. And the final rule is CC can be dropped entirely. So if we ever get two C's together, we can generate them, we can essentially delete them. And the challenge is, the problem is, can you derive AC from AB given those limiting conditions? Okay? So again, I've said any B can be replaced by BC. And in fact, BBB can be replaced by C. Any letters to the right of A can be doubled, and CC can be dropped entirely. The answer here is a big, fat, resounding no. And the reason is, as indicated on the screen there under my picture. One is that we start with one B in that situation, and there is no rule that generates Bs. And therein lies the problem. Okay? We can get BBB, but we can't get simply a B. So given that set of 4 rules, there is no solution that is possible as long as you stick to the premises, as long as you follow the rules in that situation. Or my favorite, which is another illustration of this kind of thing, is the following. It's referred to essentially as the 2 boards problem. Page and Simon in 1966 created this gem. And in essence, it's the following. Given the following, okay, one board was sawed into 2 pieces. That's the premise. And the helpful information we're going to give you is that board A is 2/3 as long as the whole board. And board A itself is exceeded in length by the second piece, which is 4 feet. And the problem then is, how long was the original board? Given the premises, there is no solution to that, and let me show you why. Because in essence, we start with this board, okay? Whatever length, doesn't matter. My markers there are 1 foot long in length. So we cut that board in 2/3. The board, as I said, premise A has now been met, okay? One board is 2/3 the total length. But the problem is, the second board was 4 feet longer than the first board, which means that board B, as we've created it in accord with the second and third premise, when you put it all together with board A, produces something that is longer than the starting board. And thus it is an impossible problem to solve. And again, the logic that's involved there is simply that board A, the problem is that board A is 2/3 the total length of the starting board, and board B is 4 feet longer than a board which was 2/3 the length of the entire board, which is essentially an impossible set of premises. That's the difficulty in that case. And what's being illustrated here then is that the logic within a problem can be very precisely stated. That doesn't necessarily mean that if you follow all of the rules dictated by a particular problem, that you're going to generate an answer, or that you can generate an answer. So basically, when we look at both of these last 2 problems, the 2 letters problem, A and B deriving AC with a series of limiting conditions, and the 2 boards problem, two boards problem where we saw one off 2/3 as long, and then add 4 feet and make that the length of the second board. In both cases, the solution resides in metacognition. That is, they are logically unsolvable in the way they are posed to us, and so we really have to step outside the loop and look at the logic of what's involved. The problem cannot be solved in one case because there is no rule that allows you to derive B's, and in the other, or C's, I mean, and in the other case, there's no rule, there's no way that you can create a board 2/3 as long and a second one that's 4 feet longer than that and have it add up to the length of the original board. Another example of this was identified by Benjafield in 1993, and this will sound familiar, but if you think about the concept of half-sister, your half-sister shares with you either your mother or your father, but not both. And that should ring a bell in terms of what we were just talking about a couple of minutes ago. All of these bear in one way or another on looking at, you have to step outside the problem and look at the information that you've been given and then see whether it is logically possible to actually derive the particular answer that's necessary in this case. So all of what we've been dealing with here is what's called deductive logic. Okay? Deductive reasoning. And I want to come back and give you one more shot at this because there's an interesting qualifier. And she argued essentially, Leda Cosmides in this instance, rather interestingly. What she argued in favor of was an evolutionary view of both cognition and reasoning. She's retreating into cognition as an explanation for what is actually involved in this situation. So what she's essentially going to argue is that essentially, the question she poses is, what might cognitive skills add to our individual ability to adapt to the environment that we find ourselves in, especially when it's a changing environment, okay? As it is increasingly occupied by cognitively wise or increasingly bright individuals, what might cognition actually add to us? In other words, what is the selective advantage to actually having cognitive skills? And taking that premise, essentially what she does is to argue that humans from the earliest times were hunters and gatherers. And so from agriculture through the Industrial Revolution, there has been a steady progress in favor of cognitive processing in one form or another. So if you look at cave paintings that go all the way back to prehistoric times, what you see depicted here is a stampeding herd of deer driven by beaters who are confronted by the deer, are confronted by a line of bowmen. What it represents is an example of cooperative hunting from a Stone Age rock painting that is on the walls at Cueva de los Caballos, I should say, in Spain. That painting is thousands of years old, but what you're already seeing, and it's a little hard to see because of the way it's cropped, but there is a beater up at the top here in the diagram. I don't know when my pointer will go there. There's another one implicitly here, and there's definitely one here over on the right that you can see a little bit of. But in fact, it's a cooperative adventure because the bowmen are over here taking advantage of the deer that are charging toward them. Communication is vital in that kind of a situation, or it won't work. And then we go to the other extreme. And that is if you look at when the last rail was laid at Promontory Point in Utah in 1869, for the very first time there, locomotives from the Central Pacific coming to the west and the Union Pacific coming to the east touched for the first time, both having arrived there by rail. And what was completed then was a rail link-up between the east and the west coast in the U.S. for the very first time. And as a result of that, immediately, the Union Pacific flooded the entire country with posters advertising the fact that you could hop on a train in the Midwest and ride all the way to the West Coast and get there, not worrying so much about people that didn't want you to get there and a variety of other things. But it was a significant link in the country and a cog in the overall Industrial Revolution. But Cosmides' point is essentially that from the very earliest times we were hunter-gatherers, but much more recently we began to rely on formal agriculture and organized hunting, and the product of that then was our movement fairly rapidly in the 15, 16, and 1700s into the Industrial Revolution. And it's on that basis, kind of the cumulative effects of that Noam Chomsky stirred psycholinguistics intellect when he really fired off the idea that we have an inherited mechanism that permits extraordinarily rapid mastery of language. They are using that progress and the value that language would play in being able to communicate, whether it's by waves and arm flailings or whatever. But the hunters who could communicate with each other drives them in this direction. We will be here. All of that was greatly aided by language. And so what Cosmides is arguing is that we're born with a schema acquisition device that allows us to abstract and organize the pertinent information from our experience into helpful units. And that schema acquisition device then is really the key, genetically inherited in that situation. One of the things that's very helpful to hunters and gatherers, she asserts, has been concerned, as an example, with social exchange theory. There, we tend to use language. So, for instance, we can ultimately do cost-benefit analysis, and our survival, even in today's world, is really predicated on our ability to do cost-benefit analyses in any given exchange. The two questions that we're constantly trying to assess and answer are, do I benefit, and am I being cheated? So you go into a car dealer here in Houston, they offer you a price, and of course the standard answer is, no, I can't afford that, whether you can or not. You're just not going to pay their initial asking price, because if you do, their profits go way up, and you have to work a lot longer, 72 months instead of 60 to pay it off, or 84 instead of 72. So you and I are constantly using language to do cost-benefit analyses, and this whole element can be described in terms of basically social exchange theory, as an example of a genetically derived theory according to Cosmides. And the assertion, I think, bears some degree of element of correctness in it. That is, it makes sense logically that we would have learned very early on the benefits of language were immediately obvious to those who gradually mastered it, perhaps 1,000,000 years ago, 1,000 years ago, 10,000 years ago, a long time ago. In any case, the advantage was there, because we could now start processing, I've got this many bushels of grain, he wants to give me a cow. Do I benefit from that, ultimately? And so it's the cost-benefit analysis in the broader context of social exchange theory that provides a good degree of intellectual justification for the inherited nature of language and language acquisition. It's inborn in us. It relates to social exchange. Even permissions, obtaining permissions from people, are also based on intellect, on processing of language, and all of the abstract principles of deductive reasoning, Cosmides is asserting, are based on inherited language and the skills that we inherit from our parents, our grandparents, and so forth. So she found social exchange theory predicted much better various kinds of solutions that we could create, which in turn bumps us right into a second form of reasoning, which is where we'll start now with our next section of logical reasoning, dealing with syllogistic reasoning. And we obviously start in this case with a definition. Syllogistic logic is also referred to as Aristotelian logic, which is another way you will sometimes hear this dictated. It's older than other forms of logic, and what you and I have to do has been the way in which we do this has been widely subjected to psychological research. It'll take me a while to get to the point where I can justify that particular statement, but syllogistic reasoning has become the object of a great deal of study by psycholinguists, philosophers, logicians, and so forth. We start with a syllogism. A syllogism is essentially deductive arguments that involve conclusions drawn from two premises, I guess I should say there, summarized most recently by Sternberg in a 2006 book. Two premises are assumed to be true, and a conclusion drawn from these premises is another way to define it. This is in Matlin's cognition book, which we use in the course here. Interestingly enough, that's a looser definition than the one that she included in her fourth edition back in 1996, when it was, which did not require a conclusion to be drawn from the two premises. A deductive reasoning task consisting of two statements that are assumed to be true plus a conclusion. She's added that, which really further restricts what we mean by a syllogism. And in fact, as you can see in Sternberg's definition, he does include the necessity of a conclusion. That really is the technically more accurate definition of a syllogism. And the other thing that's going to be related here, which we're also going to be talking about, is a premise. A premise is essentially a proposition about which an argument is made. It covers a wide range of possible sins, but we'll get into some of those to show you what's involved. The goal here is basically to produce reasoning which is not inconsistent with the underlying logical forms that are used when the premises are all fully specified. So what we're leading into is we're going to lay out a series of premises, and then we're going to reach logical conclusions derived directly from those premises so that the nature of what we're talking about here shifts slightly. Each premise constituting a syllogism specifies a relationship that exists between two categories. And I'll show you several examples of this coming up here. So syllogistic reasoning is sometimes also called categorical reasoning, which is another phrase that you'll sometimes see. And it can come in a variety of different forms. So we'll sometimes call it, you may hear this also called categorical reasoning, but it is all a form of what I'm going to call syllogistic reasoning. We're also going to start using things that you're probably afraid we were going to eventually get to, and those are what are referred to as Euler's circles. These are not referencing the Houston Oilers, but rather somebody years ago who developed this particular kind of graphically representing the logic or the premises, the combination of premises that we're dealing with here. It's pronounced that way to talk about the graphic format that is utilized here, which can be very beneficial to understanding what's going on. In fact, it will illustrate graphically, logically, what can or can't be stated. So let me give you an example here. The simplest of these is what's called the universal affirmative. In that particular kind of statement, I'm going to make a statement such as, the premise here is, all A are B. Fairly simple, very straightforward, and the most universal of the statements. Well, I should say among the most universal of the statements that can be made. Simply a universal affirmative. All Cougars are loyal alumni is an example of a universal affirmative. Another example: all isosceles triangles have two equal sides, which is going to become the basis for a rather challenging demonstration here a little bit later. All A or B can be represented or depicted in the following way. Okay? All A or B is certainly true in this particular situation. But what this diagram implies correctly is that there may be some B's that are not A's. That is, what I'm saying is there may be loyal alumni who are not Cougars, which is true. UT alumni may be loyal, may not be, but they're not Cougars for sure. But there's another possibility. Given Euler's circles, there's another possibility. What if all people who are alumni are Cougars? Then the situation would be as follows. That one we've got. But what about this one? If the A and B circles are exactly identical in size, I can still say all A are B. In this case, it is reversible. All B are A under this unique situation. The point then is that essentially all A are B can be understood in a number of different ways, and that's one of the advantages of using Euler's circles. It begins to scope out or show us visually what can or can't be and what is involved in that particular situation. So both of these diagrams are described accurately, or I should put it the other way around. Both of these diagrams depict accurately the consequences of a statement such as all A are B. The underlying point and the purpose of the circles here is to show you that in some situations this may be reversible. Certainly in the right-hand situation there, we can also make the counter-assertion all B are A, and that would likely be included in the initial premises when we're setting up a particular argument situation. But the circles on the left also depict all A are B, which opens up some other possible conclusions, which is my point in raising that issue. Let's go the reverse and see what happens. Now let's start with a very different situation, and that is the following. Let's do the universal negative, okay? No A are B. No Cougars are Aggies. Or I guess to be more current, we should say something like no Cougars are Cardinals, Louisville Cardinals. Or no Cougars are Bells, Memphis Bells. To be currently accurate, I should say. No right angles are less than 90 degrees is another example of a no A or B kind of assertion. No A or B can only be represented in one way. Okay? That's this. For this class, and for this class only, there's only one way that this can be interpreted, and that is there is true reversibility here. The reverse also has to be true. If no A or B, then by logical example, given Euler circles, it has to be also true that no B are A. So where all A or B may or may not be reversible, no A or B is totally reversible. If the one statement is true, then you can reverse the A and B, and the statement is still equally true, as indicated by the circles here. There are two other universals that we can talk about here. The third is what's called a universal, a particular affirmative, is what I was moving toward here. We could say, for instance, some A are B. Now you get into an increasingly complex diagrammatic situation here. Some cougars are women. Fits perfectly with the some A or B as an exemplar. This one is much more complex in that there is not one, but actually four possible ways in which to interpret this statement. Diagrammatically, we can represent it as follows. Okay? This is actually true in terms, or is an accurate description of, some A or B. Now you and I look at that and say, well, all A or B in that situation, yes. But that's not excluded by the statement some A or B. I'm going to come back and talk about what we mean by some in a couple of minutes here, and that's where the hang-up is with this particular one. But that's a true diagram of the assertion some A or B. It's true. It's just you can't find the reverse, which is any A which is not a B in that situation. That isn't what's stated by some A or B. It simply says some of them are A. Well, some in this case happens to be 100%, which is diagrammed on the left. Let me show you another one. This is another example of where some A are B. Again, that understates what you and I can see is the case. We could also clearly say all A are B, but it is legitimate to say some A are B, given the second situation. We get a warm feeling behind our belly button when we look at something like this. This looks a lot more comfortable to us, okay? Some A or B much more clearly means this. Well, no, not really. It depends on your definition of some, but certainly the third diagram there is a situation where some A are B, and obviously in this case, not all A are B. And finally then, we've got the most comfortable of all, which is this, which clearly implies some A are B. Here, the reverse is true. Some B are A. So you can see that under some circumstances, these are reversible, but under many conditions, this situation is irreversible. That is, you cannot, because some A are B, make the assertion correctly that some B are A. There may not be that necessity of truth required there. So this becomes much more difficult to interpret intellectually and logically, and that's the reason these circles become essentially very, very beneficial to us in keeping track of what we're talking about. And finally then, let's look at the last one, which is essentially what's called the particular negative. You can predict where this one is headed. Some A are not B. Slightly more limited ways to diagram this. There are three possible interpretations that can be made in this situation. This is one of them. Some A are not B. Well, again, that's an understatement of what this diagram actually depicts, as you can see, because here we can also, as we said earlier, no A are B, or all A are not B in this particular situation. So in the particular negative, we could say some cougars are not women. And here there are actually three possible interpretations. This one is one. There's a second one that looks like this. Again, some A are not B, as diagrammed in the center diagram. And again, you can see why we use that. And the final one then is this one, from what we described earlier. This is a direct extension of what we were looking at a minute ago. And in this case, again, some A are not B, in the situation that we see on the right side there. Okay? So in this circumstance, the statement can be reversed. Some women are not cougars. But there are also situations where the statements can be interpreted so as not to be reversible. Some animals are not sheep is true, but that does not mean that some sheep are not animals. So it depends on the specific instances as to which of those three diagrams actually applies in a given situation here. The logic in this situation can become quite complex. Some Iraqis are not field hockey players. As a statement leaves us with the following. It may be that some Iraqis are field hockey players. We're never going to know. We just will never know. But it is not logically necessary that some Iraqis play field hockey just because some of them don't. And that last implication is where things begin to really stack on in terms of the complexity of what we're dealing with here. This last set of statements opens the door for the primary reasons why psychologists are interested in such syllogistic reasoning strategies. They become very important in justifying why psychologists are interested in this. It's because of the cognitive limits imposed on us and the things that they enable us then to study from a logical perspective. In essence, then, this is the intrusion of world or background knowledge. Let me back up a little bit because I didn't want to jump to that conclusion yet. Let me suggest that there are two general statements that are true here, two general statements that can be made about what we've done up to this point. Reasoning logically requires that you reach only those conclusions that are possible given any of the logical interpretations that can be properly attached to the premises. The premises. I keep mispronouncing that. Okay? When you state your if A then B or if, whatever, once those are stated, what are the logical derivatives from that can be defended in terms of logic? And so we can only use logically defensible conclusions in this situation. And the other limiter that is involved is that basically we do not actually work out all of those interpretations. This is where the psychologist becomes more interested. Because our reasoning is based on procedures that are governed by how the premises are encoded, but not always. It's limited by that. But our experience tends to be that we can go from the given to an obvious conclusion without necessarily working out all of the logical implications. And it's how we do that based on experience that really justifies why we end up spending so much time looking at these. What this leads to then is an examination of what kind of errors do we make. When we engage in syllogistic reasoning, where do the errors come from? And this leads to a rather interesting series of studies. If we look at errors in reasoning, the problem that we have is essentially the correctness of the conclusion depends only on whether the conclusion follows logically from the premises. And that's all. The actual truth is irrelevant when we're dealing strictly with these logical premises and what they permit versus what they don't permit. We naturally tend to have difficulty separating our beliefs from the logic of such forms of argument. We go into it believing this is true, this is true, this is true, and then all of a sudden our logic tells us, well, wait a minute, not always. Or no, this isn't true, in the extreme. We may accept things that we believe to be true, or reject things that we believe not to be true, regardless of the underlying truth, the underlying extension of the logic of reasoning that we're actually using. And so what I'm trying to separate here is logic from belief. Those two are separable commodities. Sometimes they work to our benefit, sometimes they do not. And so this is where we really start talking about the fact that your real world of experience or the background knowledge that you carry into any situation becomes a limiter. In some situations, it will permit us to see some things. It will actively discourage us from seeing other things, even though logically we could demonstrate this has to be true. If you give this follows as an absolutely logical conclusion. And so in essence, this becomes why we start looking at when things are invalid or when real-world beliefs begin to intrude on and, in fact, functionally limit the way in which we solve particular kinds of problems. So what I'm doing now is kind of bringing together two different kinds of things. One is the logic, the cold, hard philosophical logic, starting from all A or B and so forth, what those imply by way of what we can derive by way of conclusions, versus our world of beliefs and experience, which are another pragmatic source impacting when you and I decide to do or not do something, when we decide to believe or not believe something. Okay? One of the classic examples of this is essentially an illusion. And so what I'm going to pose to you here is something that you may have seen previously, and it always runs me buggy as somebody who scores high in the math potential on exams. I've always scored high, and I've always had trouble with this particular diagram. This is what's called the Sanders parallelogram, the Sanders parallelogram. Okay? What is asserted here, and what can be demonstrated mathematically, and you'll have to follow me closely on this, is that angle CAE, that is the angle generated by this, here, left turn, CAE, this angle right here, is the same as ACE, which is the angle generated by this line to C to E. So what's being argued is this angle is the same as this angle. That's the assertion. Okay? We know from math logic that if two angles are equal, if two angles of a triangle are equal, by definition we have an isosceles triangle. And thus the sides opposite those two equal angles are themselves equal. Are you with me on this? I don't want to blow anything past you here. Nod yes, I understand. No, I don't have a clue what you're talking about. Okay, I'm getting generally positive nods. We'll press on. So what's being argued here is essentially that AE, being opposite ACE, the angle, is the same length as CE, which is what's opposite the CAE angle. We're arguing then that we've just proved mathematically, by assertion, that this line is the same length as this line. Does it look that way? It sure doesn't. I'm going to go ahead and do this. My jumpy hand is going to give me a little bit of difficulty, but I'm going to back out of the program and show you. I couldn't believe it when I looked at that. I drew it all up, and I still didn't believe it. But give me just a second here to do what I'm going to do, which is to take this particular object. Bear with me a minute. You can watch on the screen what I'm doing. It won't hurt. What I'm going to do is to copy that. Okay? So now we've got the same thing doubled, if I can make it work here. Come on, let me copy this. I want to copy that and reproduce it. Now what I'm going to do is to allow myself to rotate that, which means I'm going to go into Draw and talk about free rotate. Whoops, the system doesn't have it. I may not be able to do that for you. Well, in a word, phooey. If you do this on your home computer, if you copy the screen and put it on your home computer, let me just back up here. We will go back up to File, Save As, and we'll make it whatever. Yes, I wasn't going to be able to do that. I actually did that and rotated it myself. I'll have to leave it there, but I'm almost done with this picture, so let me get back to where I was going originally. Should have tried that out before I did it. There we go. That's what I needed. If you actually copy that diagram and rotate it, you can then lay line EC right up on top of AE, and in fact they are equal distance. Okay? So there's a case where logic can actually be used to work out of the problem caused by illusions, which is a perceptual problem that we actually have here. This disagrees with our senses, but it's logically and empirically correct. And the best way to do it, maybe to convince yourself, is just copy the diagram and then rotate it as I tried to do there. Okay, that's the one we don't need. And so now we'll move on to a couple of different types of errors in reasoning. One of these is the basis for establishing these errors. One of them is what's called an atmosphere effect, of which I can give you several examples here. But Woodworth and Sells suggested some premises create an atmosphere which fosters certain type of reasoning errors. Some premises create an atmosphere which encourages reasoning errors. One example that they cite is the following sequence, and I'm sure you've heard something like this before. Some A are B, assertion 1. Some B are C, assertion 2. Therefore, some A are C is not correct. Okay? That sequence, some A are B, some B are C, therefore some A are C, is not correct, and we can use the circles basically to demonstrate this, or I can give you a logical example. Some men are Texans, some Texans are women. Therefore, some men are women, which just doesn't work, okay? We could debate that a little bit, but essentially, there's no way you can get from A to B to C in that logic, and therein lies the problem with the sum difficulty. That is what these premises, some A or B, some B or C, therefore some A or C, sets up what is called a sum atmosphere. You're kind of thinking in terms of illustrations that will work, which encourages the acceptance of some sort, the acceptance of a conclusion of some sort, pun intended. Another atmosphere which can be established is a negative atmosphere. No A or B, no B or C, therefore no A or C. Diagrams representing both of these last two situations are like the following. Okay? There's a situation diagramming one of the instances where some A or B, some B or C, and therefore some A or C is clearly not correct. That would be essentially a representation of some men are Texans, some Texans are women, and so forth. And it shows you that to be in A and related to B is not to be in C and related to B. And the second one I was talking about, no A or B, all B or C, no A or C. Is illustrated by this. That's one example of where that sequence will not work. Here's another one. No A or B, but in that case, no A or C doesn't apply. So in essence, atmosphere effects can bias the way in which we get on a roll, some this, some that, therefore some the other thing, doesn't necessarily follow. And that is essentially described as an atmosphere effect, where you start thinking in terms of some, and yeah, you can come up with situations where that would be true, but there are equally counterexamples that demonstrate that it is not universally true. A second type of problem that we may stumble into is what are called conversion errors. Chapman and Chapman in 1959 talked about illicit conversion of premises. That is where we try to convert a given premise into another consequence that may or may not be true. Remember, we talked about at least two legal conversions, okay? No A or B, and therefore then no B or A. That works. That's true. And it's also true that we can talk about some A or B, and in that case, some B or A. But notice, all A or C, all B or C, therefore all A or B in this situation doesn't work. It's a conversion error that has occurred in that kind of logic. The one does not justify the other. The premises don't allow that conclusion to be drawn under certain circumstances. Excuse me. This same diagram we just used a couple minutes ago to depict this situation, and it shows an example of why it cannot be true. Okay? Begg and Denny in 1969 showed that both the atmosphere hypothesis and the conversion hypothesis predict similarly as to what types of errors will be made in syllogistic reasoning. The logic of sum and the logic or the illogic of conversion in certain cases leads us psychologically to predict why we may make those errors, even though we can demonstrate that they are errors, or I should say that we commit the errors, even though we can demonstrate that they are in fact errors. They're not allowed by the logic that was involved. I said I'd come back to it. Let me just deal specifically with one of the primary examples of why this is happening, and that has to do with our understanding of what we mean when we use a word like sum. If you actually, and it's cute to do this, you go into a big introductory class, such as I often teach, and you ask people to define what do you mean when you say sum? you know, some apples are rotten in a basket of fruit. Okay? What does that actually tell us? Does that mean, because logically we've just shown you that that could mean every single apple in that basket is rotten. But you and I, given our experience, don't tend to think that way or don't intend that when we're looking at a basket of apples and saying some of them are rotten. We generally mean some proportion of it. And if you look at, across large numbers of people, what they mean by some, what they're really referring to is, and what's generally meant is, 51%. Now that's a little overstated, but it means essentially a majority. When you and I talk about some of, we're generally talking about more than half. Some of is what we're really meaning, but that's where we have trouble when we start getting into the logic of what's actually involved in principles that involve some this, some that, some the other thing. Okay? Some people are human. Well, logically that's true because some includes all. But therein lies our problem. It implies that some people are not human. But that's not what's stated. When you say some people are human, what you're actually implicitly saying logically is all people are human. But that seemingly more limited statement is allowed given the logic of some people are human. Some normally is interpreted to mean some but not all. Logically that's not correct, however. The problem in common usage, let me state that again. The problem is common usage versus use in logic. Okay? That's where the difficulty resides. Bagg in 1987 told subjects a group of people consists of 20 artists and 80 writers. Hang with me a minute because this gets a little bit complex. But the logic here is that some means some but not all as we commonly use it, which is not actually correct. And here's the situation. Okay? In one study about 20 years ago, subjects were told a group of people consists of 20 artists and 80 writers. So the writers represent 20% in this group, and the writers represent 80%. Half of each group are men, half are women. Why they had to be told the second half, I don't know. And so what we can do then is to divide each group in our total circle of whole in the following way. Among the artists in green, half of them are men, half are women. And among the writers in, what is that, light blue, half of them are men and half are women. We can say some men are artists and some men are writers. We can say from this some women are artists and some women are writers. So far, so good. The statements identifying more limited classes were rated as more acceptable. That is, when they were given statements like the ones I just gave to you, people were more willing to accept that than statements that were more arbitrary. One of our uses then is to the idea that some generally means less than half. That's one of the uses that we sometimes put it to here. But let me just read you what Webster actually says about some. The official English-based definition of some is being an unspecified number or part. Unspecified number would allow the whole. But adding that tagline or part kind of implies, as we're talking, when we normally use the word some, we're talking about less than the whole, even though logically you can be talking about the whole. A second definition is being unknown or unspecified by name. Some may include all. It's still logically possible here. And then in terms of logic, Webster also defines some as being part and perhaps all of a class. It's that third definition that hangs us up and gives us all the difficulty with, not all of, but some of the difficulty that we have with communicating in terms of logical premises. That is, we conclude that our normal use is useful for successful communication, but its use in logical communication and logical argument may lead to imprecision in the process, and that is exactly what we find happening in this particular situation. Another way to look at this is to look at mental models, which is a variation on the atmosphere effect. as we were talking about it. Johnson Laird has studied the mental models that we developed to represent syllogisms, the circles, among other things that I was showing you earlier. And decisions, he argues, are basically based on checking the conclusion against the models that have been created. So instead of working logically through what's possible using Euler's circles, for instance, what you and I tend to do instead is to take a given premise and compare it against our knowledge, our understanding of the world of which we are a part. So we take our life experience, picture whatever has been stated as a premise in those terms, and try to reach conclusions based on that. Sometimes well, sometimes not so well. So what Johnson Laird is arguing is that our decisions are based on checking our premises against the model that we've created. The shortfall there is the model an accurate representation? And you might have seen with Euler's circles when I was showing you the diagrams that were legitimately allowed by some of the assertions earlier, don't necessarily square with what you and I would think of as a model of that particular process. Johnson Laird's particular focal point was studying inferences about mental representations in syllogistic reasoning. That is, what decisions do we reach based on the models that we create here? The first premise, then, that we're going to practice with here is the following. We're going to use this as a variation on the atmosphere effect and show you the following model from which we infer our logic and thus predict our conclusions. Let's imagine the following statement. All applicants are banana lovers, which allows us to create an argument or a model, something as this. The statement then is all A are B. All applicants are banana lovers. I've even made the letters consistent with the illustrations to make it easier for you here. So our model might look something like this. All of the applicants, little letter A, are, and we could interpret that arrow as essentially are identical with, if you want. The arrow means are identical with or equals B, which is banana lovers. Okay? The difficulty is caused by the following. We've got some other banana lovers here. I've just thrown that in for the sake of argument here, and you'll see the difficulty that it causes for us. So the second assertion is some banana lovers are cute, which allows us then to do this. Some B are C. So all A are B, some B are C. And therefore, can we conclude some of the applicants are cute? You can see where this is headed. So therefore, we're arguing all A are B, some B are C, and therefore some A are C. But the difficulty is the banana-loving skills are still there, but there's an example of a banana lover who is cute, who is not an applicant. And in the model that we've created there are no applicants who turn out to be cute in that situation. So in essence, we're led into a kind of an interesting series of short circuits, sometimes depending on the kind of model that we have actually developed. The point is that you have to consider all of the models. When you start using Euler's circles, you have to be aware of all the different formats that it can take before you can really start using it logically to help you with the logic that's involved. Now here comes the psychology, not just the logic, but the psychology. Let's look at, well, I'm just restating the obvious here. That kind of a model may lead to erroneous conclusions. Point made. Point over-abused. Let's look at a couple of things that do impact how we make these models, what we develop. One of them is imagery that we talked about quite a bit earlier, and relatedness, which I'm going to define for you here in a minute. Okay? Imagery we talked about way back in tapes 10 and 11, lectures 10 and 11, and we were talking there about the richness of, or the ease of creating a mental picture for any kind of a concept. And the example I gave you was apple, which creates a very easy concept, versus a word like truth, which tends to generate as many different images as there are minds in the room here. Okay? So imagery is one of the things we're going to vary here. And then we're also going to manipulate the relatedness of what is involved. And I'm going to define relatedness essentially as a measure of how easily or naturally two actions form a relationship. You might insert logical relationship there, but form a relationship. Which leads then to some rather interesting assertions. So if relatedness deals with how easily or naturally one action leads to another or links to another, we start with the following kind of situation. I could make a statement such as, if a woman wants a new red dress, then ... And in that case, what I've given you is a high imagery statement. You can easily imagine a woman desiring a new red dress. Not hard to imagine. I can give you low imagery. If the man reorganizes his thoughts, then ... That doesn't necessarily draw the same image to mind for each of us. So that's got low imagery. But what's the relatedness here? If we talk about a high relatedness statement coming out of that if-then sequence, we might give you a situation like high relatedness. If the woman wants a new red dress, then she walks to the dress shop across the street. You notice the gap there in the error word that I made, strop. I was anticipating street as the word that I was leading to there, going back to an earlier lecture. Okay, that's an example of a high relatedness statement. Okay, high imagery. If a woman wants a new red dress, then she walks across the dress shop to the street, across the street to the dress shop. The heck with it. I'm not going to use that again. Or I can give you a low relatedness. If the man walks his greyhound, good imagery, then he gets angry about his bug bite. What? That could follow. I mean, if you're walking in upstate New York in March, you're going to get bitten by bugs. Well, April, since they're snowing this year in April. But in fact, bug season in New England is late March, early April. So there is some logic there if you happen to be in upstate New York or New England, but not necessarily here in Texas. There are times to walk and not to, but that's not an A statement that leads directly or relates directly to a B. So in this particular study, all four combinations were used. That is, as indicated in the table there, low imagery or high imagery linked to either low relatedness or high relatedness, the high being wants a red dress, goes to shop down the street, so I can do it correctly. And what was found, interestingly, in this kind of combination of imagery and relatedness was a rather, well, maybe not surprising set of results. Syllogisms that are high in imagery and high in relatedness solved significantly more often than other forms. That is, the syllogisms based on those kind of linkages, those kind of limiting premises, were solved more rapidly than situations where either the imagery or the relatedness was low. And that there were forms of syllogisms leading to more graphic models. Okay? That the syllogisms that led to the most imagery-rich models tended also to lead to the best solution. We saw that earlier when we looked at the fog problem versus the naming problem or the two sisters problem that I was talking about with you slightly earlier. So then when we start looking at the logic and coming at it as psychologists, asking essentially the question, what leads to these kinds of situations, we begin to develop some fairly defensible answers as to why particular kinds of logic lead us either into good or not so good conclusions. Another thing that we can look at is also the content of the statement and the accuracy of the conclusions that we tend to reach. This was a diagram or a demonstration of factor suggested by Salso in 1995. He suggests a rather interesting illustration, and you'll see the problem here in just a minute. We argue all men are moral. So that's our initial premise. All men are moral. We also argue Socrates is a man. Therefore, Socrates is moral. Did I say moral? I meant to say mortal. Okay, let me redo that. Again, I'm anticipating, but I'm a paragraph ahead of myself here. All men are mortal. Socrates is a man, therefore Socrates is mortal. We have no problem with that. Okay, that agrees with our observation, it's accurate, and the content is okay to us. But we have no trouble agreeing with that. But how about the following? All humans are moral. Now I do mean moral. Okay? Kim Jong-il is a human. Therefore, Kim Jong-il is moral. Now we're talking about the leader of North Korea, who at the current time as a nation is quite isolated because they're simply not willing to work with the rest of the world on production and potentially ultimately release of nuclear energy, nuclear products in particular kinds of situations. If the premises are true, then the conclusion is two, though it is somewhat more difficult to accept the second than it was the first in the pair that I've just given you. It's easy to argue all men are mortal, and thus conclude that, Socrates was a man and he was mortal. But to talk about all humans being moral, if Kim Jong-il is a human, then he is moral. Okay? That's the difficulty. In other words, what's being fought here is the accuracy of the assertion versus the derivative accuracy of it, whether we can justify it in terms of the logic that's actually involved. The conclusion then is that what you have to look at in order to argue in logic is the soundness of the premises. Okay? I'll make that in another way here in a couple of minutes, but in essence what we want to do is to attack the premises, not the conclusion. If you grant the premises, all humans are moral, Kim Jong-il is a human, those two combine to force you to conclude that Kim Jong-il is moral. If you've granted the two premises, the conclusion has to follow. Therein is the problem, and what that also suggests then is an argument strategy. When things start falling apart, attack the premises, not the conclusion in that situation. Which leads us then to another psychological concept, is the word I'm looking for, to talk about, and that is soundness. We're going to define soundness essentially as a conclusion that logically follows from the premises. Okay? All poisonous things are bitter. Arsenic is not bitter, therefore arsenic is not poisonous. You heard it here for the first time. Now, in that situation, clearly I'm blowing hot air with no particular benefit in this situation, because the logic, the soundness of the conclusion is falsified by the unsoundness of the premises in that particular situation. Graduate students were asked to agree or disagree with each conclusion in a series of premises like the pair that I just gave you earlier, and then were asked to rate their personal agreement or disagreement with each conclusion that had been reached. So they're given the if A, then B kind of a premise. A is true, B is true, is C true? And what was found was that the errors that they made in reaching a false conclusion, that is coming to a wrong answer, tended to reflect their own biases regarding the conclusion itself. That is, they were more likely to be wrong if the erroneous conclusion was consistent with their own beliefs. If you tend to believe whatever the conclusion is, you then tend to defend it as logically correct. If A, then B, if B, then C, therefore if A, then C. If the conclusion agrees with your own beliefs, you tend to not be quite so critical in examining the underlying arguments in that situation. It essentially boils down in logical terms to the idea of my mind is made up, don't confuse me with facts, which is what we get to in this particular situation. So, a couple of other errors that I can point out here that we can gauge. One is the fallacy, is what I'm reaching for, the fallacy of reification. Okay? Phrases such as, and you've heard these all on the news, the administration, the Democrats, the Republicans, Mother Nature, represent essentially personification of non-human concepts. Okay? Republicans per se, or Democrats, are not human concepts. They're an abstraction of political beliefs, not of humans. People do things, not administrations. And so in essence, it is erroneous in that particular situation to reify something, to convert it into human form, when it is in fact itself an abstraction. There's another issue that is related here, and that is what's called ad hominem arguments. This is what's called poison the well arguments, and you've heard these too. Okay? So the fallacy of reification is one problem. A second one is essentially ad hominem arguments. When arch-conservative Rush Limbaugh refers to people advocating in behalf of our environment as the nature Nazis, he is not only well into the arena of bad taste, but he is also committing the logical fallacy of using an ad hominem argument. Though I've never seen much worry about logic in his arguments, and in fact in interviews he himself has acknowledged he's not about logic, he is about maintaining and generating radio audiences. So when you keep that in mind, he's a lot more fun to listen to than trying to find any consistent theme in what he's arguing. His goal is to sell things of his sponsors, period. But in any case, that kind of a nature Nazis as a phrase is an ad hominem attack on people who are in support of advocating for maintaining our environment, for doing more things to maintain our environment. You can argue with the messenger rather than the message. That's the error that is being created there. You attack the person rather than his or her argument. That is essentially ad hominem argument, and it's a bad form. It does not win arguments. Related to this is the N of 1 problem, and you'll see the link here in just a second. Students who react negatively to a statement I make will sometimes offer up arguments like this. In the developmental section of my 1300 course one time, I had made a statement about the fact, which is defensible in terms of the data, the first word is normally spoken at about 12 months of age, which is true. As we've talked earlier and as we'll talk again later, the inability to document exactly when a word is used for the first time makes it difficult to nail exactly when it happens. But the general statement is true, based on data. And sure enough, I had no sooner gotten that out of my mouth than a hand went up in the back of the room and said, "You're wrong. My daughter spoke her first word when she was 10 months. As if every child will do that. But that's an N of 1 argument. It isn't excluded by my use of the word most. But in fact, it is a basis for counter-arguing. And people do that fallaciously. We're going to talk next time about appeal to authority or fame, and we'll pick it up next time getting into inductive reasoning.